where we are literally shrinking ourselves down to the nanoscale. We're talking about a world so incredibly small that a single sheet of paper is, well, about 100,000 times thicker than the structures we're looking at. When you're engineering materials at that scale, whether you're working with nanoparticles, super thin films, or next-generation microchips, you can't exactly just whip out a magnifying glass, right? You need highly specialized eyes. So today, we're exploring one of the absolute workhorses of the nanotechnology world: Energy Dispersive X-ray Spectroscopy combined with field emission scanning electron microscopy, or, as it's thankfully known for short, EDS with FESEM.
So here's our roadmap for today's explainer. First, seeing the nanoscale world. Second, how FESEM and EDS work. Third, the superpowers. Fourth, the kryptonite. And finally, number 5, the final verdict.
All right, part 1, seeing the nanoscale world, the ultimate tools for tiny tech.
You know, when you're engineering at the atomic or molecular level, it's just not enough to only see what a structure looks like. You need to know exactly what it's made of, right down to the individual elements, and you have to know exactly where those elements are located. Let's quickly define our terms for the tools that make this awesome dual-threat capability possible. First up, FSM, or field emission scanning electron microscopy. Think of this as your ultra-high-resolution camera. It gives you insanely detailed topographical images of nanostructures. Then we have EDS, Energy Dispersive X-ray Spectroscopy. This is essentially your chemical interrogator, giving you rapid elemental analysis. Put them together and they form this absolute powerhouse system, combining physical imaging with simultaneous chemical mapping.
Moving on to part 2, how FESM and EDS work, the anatomy of analysis.
To really get how this all comes together, we need to trace the journey of a single, highly energized beam from its source all the way to the final data readout on a researcher's screen. The whole technique boils down to 3 really elegant mechanical steps. Step 1. A highly focused electron beam is fired at the nanomaterial sample, exciting its atoms. Step 2. As those atoms settle back into their normal state, they release energy in the form of X-rays. And here's the magic part. Those X-rays are perfectly characteristic of the specific element they came from. Step 3. The EDS detector catches those exact X-rays and translates them into a map of the elemental composition. Imagine this whole brilliant setup in action. Picture the FESEM column. At the very top, you've got the field emission electron source generating the beam. That beam travels down, passing through these condenser lenses and an objective lens, which focus it into a brilliantly sharp point. Boom! That electron beam strikes the sample sitting on the stage at the bottom. As the beam hits the nanomaterial, characteristic X-rays go bouncing off and travel directly into the EDS detector that's pointing right at it. From there, all that data flows into the computer, and we get a beautiful, high-resolution FESEM image of the nanoparticles right alongside a super detailed spectrum.
In that spectrum chart, it's basically a collection of chemical fingerprints. Because every element has a totally unique atomic structure, every element emits X-rays at incredibly specific energy levels. When you look at an EDS spectrum, you'll see sharp peaks at different energy levels, which are measured in kiloelectron volts. A peak at one specific spot means, without a doubt, carbon is present. Another peak definitively identifies oxygen, or magnesium, or gold, or silicon. The detector counts these X-ray hits, and that lets us map out precisely which chemical fingerprints are hiding in our nanomaterial.
Which brings us to part 3, the superpowers, key advantages of EDS with FESM.
So why is this specific setup such a massive deal in laboratories everywhere? Why do materials scientists rely on this exact machine day in and day out? Well, here is your high-level overview of the system's 4 main superpowers. Number 1, high spatial resolution. Number 2, simultaneous elemental mapping. Number 3, it's incredibly fast and completely non-destructive to the sample. And number 4, it requires very minimal sample preparation. Let's actually break these down a bit to see what they mean for the person running the microscope.
Let's look at those first 2 superpowers. FESEM provides a phenomenally bright, highly focused electron beam. This high spatial resolution means you aren't just looking at a big chunk of bulk material. You can literally point that beam at an individual nanoparticle or maybe a tiny 20 nanometer defect and say, hey, what is that specific thing made of? And on top of that, you get simultaneous elemental mapping. As the beam scans across the sample, you're generating beautiful color-coded spatial maps of elements like zinc, oxygen, gold, and silicon right alongside your topographical image. You see the shape and you see the chemistry, all at exactly the same time.
Superpowers 3 and 4 are really all about efficiency. The analysis is fast and it's non-destructive. You can get qualitative and quantitative elemental profiles incredibly quickly, completely without harming your super delicate nanosamples. Add to that the fact that there's little to no sample preparation needed. You don't have to submerge your samples in harsh chemicals or alter them, which means you are preserving the original nanomorphologies exactly as they are in the real world. This saves researchers an unbelievable amount of time and ensures the data is actually accurate.
But it's not all perfect. Let's hit part 4. The kryptonite, system limitations. The limitations of EDS with FESM aren't really design flaws. They're fundamental constraints bound by the laws of physics themselves. There are 4 main kryptonites we need to be acutely aware of when we're interpreting data from this machine. First is the interaction volume effect. Second is its serious struggle with light element detection. Third is the really frustrating issue of peak overlap. And fourth is its relatively high detection limits for trace elements.
Let's directly contrast our first superpower with our first limitation. You have high spatial resolution from the electron beam, right? That lets you target a tiny nanoparticle right on the surface. However, when those electrons hit the sample, they don't just stop at the surface. They scatter downward and outward, creating this teardrop-shaped interaction volume that can plunge hundreds of nanometers deep into the material. So while your beam is aimed at a tiny 20-nanometer particle, the X-rays bouncing back to the detector might actually be coming from the thick substrate underneath the particle. You might get a huge signal for a material that isn't in your nanoparticle at all, but is actually just buried beneath it.
Next up is what we can call the light element blind spot. If you picture the top left of the periodic table, hydrogen, helium, lithium, beryllium, and boron, these are low Z, or low atomic number elements. Well, EDS has extremely poor sensitivity for these. They are incredibly hard to detect. If your nanomaterials whole function relies heavily on the presence of lithium, for example, like if you're doing cutting-edge battery research, EDS is really going to struggle to give you the clear chemical picture you need.
The third limitation is peak overlap. Remember those beautiful, unique chemical fingerprints we saw on the spectrum earlier? Well, the detector has a moderate energy resolution of about 128 electron volts. This means that if you're analyzing a highly complex material, the X-ray energies of 2 completely different elements might be so close together that their peaks literally overlap on the chart. They just blur into one big peak, making it incredibly difficult to accurately figure out which elements are actually in there.
And finally, the detection limits. The crucial takeaway here is this specific range, 0.1 to 0.5 weight%. That is the typical detection threshold for this technique. If you have trace dopants or tiny impurities in your material that make up less than 0.1% of the total weight, EDS is probably going to miss them completely. It is absolutely fantastic for the main ingredients, but it definitely struggles to find a needle in a haystack.
Which leads us to part 5, the final verdict, power-bound by physics. We've seen the brilliant highs and the inherent lows of this setup. It's really a story of incredible analytical power, inevitably bound by the physical realities of electrons and X-rays. To summarize our explainer today, EDS combined with FESM is an absolutely vital, powerful technique for rapid elemental analysis and nanoscale imaging. The ability to see topography and chemistry at the exact same time with almost zero sample prep is a total game changer. But any researcher using this tool has to be a strategic thinker. You have to account for that interaction volume effect, pulling signals from deep in the substrate. You have to remember its blind spots for light elements, navigate those overlapping peaks, and accept its limitations with trace impurities. It's a masterful tool, provided you know exactly how to wield it. We are constantly pushing the boundaries of nanotechnology, building smaller, more complex, and more delicate structures every single day. The things we're creating are rapidly shrinking, but the physical limits of our X-ray detectors pretty much remain the same. So I'll leave you with this to think about. As our technology gets smaller and smaller, how will our analytical tools evolve to finally overcome these frustrating detection limits? Are we going to have to invent entirely new ways to see, or just find cleverer ways to look? Thanks for joining me on this explainer, and keep questioning the nanoscale world around you.